One more case worth reviewing because it allows us to connect to what you'll see in Richard Muller about orbits is the idea of uniform circular motion. If I swing this ball around in a circle like that, going around and around and around in a circle. And one thing to notice is that the speed of the ball is approximately constant. Actually, if I do it this way, so then gravity becomes irrelevant. So if I go in a completely horizontal circle like this, the speed of the ball is constant. But the direction in which the ball is moving keeps changing. See, the ball's moving toward you, away from you, toward you, away from you, toward you, away from you. And in fact, when it's in front of me, it's moving that way, and when it's behind me, it's moving that way. So you can see that the direction of the ball keeps changing, but its speed stays the same. So acceleration is a change in velocity. It doesn't have to be a change in speed, it's a change in velocity. So in this case, the acceleration that keeps this ball moving in a circle is not a change in speed, it's only a change in the direction of the velocity vector. So let me see if I can do it this way again. Pretend that it's moving at precisely the same speed the whole time, even though that's pretty close to true if I go fast enough. You can see when the ball is up there, its velocity points that way. When the ball is over here, its velocity points that way. So when it's over on this side, the velocity points up, but an instant later the velocity points that way. And an instant later the velocity points that way. So when it's here, see, just before it's here, its velocity points like that. And just after it's here, its velocity points like that. So what turns this arrow into this arrow is an arrow pointing that way. So if my velocity vector is pointing like this just before I reach the point where the ball is closest to me here, and if it's like that just after the ball is closest to me here, then to get this arrow to become this arrow, I have to nudge it that way. The ball is here at one instant, and the ball is here at the next instant. Here's the blue string, and then here's the length of the blue string, and then there's going to be some intermediate point here where the blue string is like this. But when we're down here, the ball's velocity is pointing that way. And when we're up here an instant later, the ball's velocity is pointing that way. The acceleration is the change in velocity per unit time. So to change this arrow into this arrow, see, if you take this arrow, if I connect that with an arrow that goes like this, and I connect them tip to tail, so you take this plus this, then those two add up to, if you want to turn this initial green arrow into this later orange arrow, to do that you have to add this blue arrow. And notice that that blue arrow points toward the center of the circle. Again, we're not going to do this in any detail because it's a Physics 8 topic, but it's just something that I'm hoping that you've seen before, even if it's not too clear in your memory. For uniform means constant speed, circular motion, the centripetal acceleration, centripetal means toward the center, equals v squared over r, where r is the radius of curvature of the circle and v is the speed. See if you can imagine the tension that I feel in the string. If I go slowly, it's a pretty small tension. Imagine if I go faster and faster and faster, you can imagine in your mind's eye that I feel a bigger tension in the string. I can feel the string pulling on me more. So I go faster, then that v squared part is bigger, and I can feel, I've said tension, because there's a force. So I can multiply this by m, and I can multiply this by m, and that's the centripetal force. So that's the force that's needed to keep going in a circle. So I need a force pointing toward the center of the circle, and its magnitude has to be the mass of the thing that's going in a circle, the ball in this case, times v squared over r. This is the speed at which the ball is going around the circle, and in this case, r is just the length of the string, but it's the radius of curvature of the circle. Here's a slow v, small v. If I make v a lot bigger, then the tension in the string, which I can feel in my finger, that's the amount that the string and I'm pulling on the string's pulling on the ball. I can feel that there's a big force there exerted between my fingers and the ball through the string. So that's bigger in proportion to the square of that speed. And then meanwhile, I can go around at the same speed. Same speed doesn't mean number of times per second. Speed means number of meters per second. If I go around at the same speed at a bigger radius, it's like if you take a highway off-ramp. Suppose you take a highway off-ramp at 30 kilometers per hour. That's okay for a highway off-ramp with a kind of a gentle bend. If you go that same speed, 30 kph, on a very sharp turn, smaller radius of curvature, it's going to be harder for your tires to maintain contact contact, because the necessary force, the force that's keeping your car going in a circle in that case is the friction between your tires and the road. So for a given speed, if the radius of curvature is too small, your tires have a harder time keeping a grip, and your tires might lose their grip because the friction can only do so much. Okay, one other result that you might remember from high school physics, but you certainly won't remember from Physics 8 because we don't do it in Physics 8, is Newton's universal law of gravitation. And Newton's universal law of gravitation says that every two objects in the universe attract one another gravitationally, and this is with a gravitational force between A and B, and this is equal to, there's some constant of nature called big G, times the mass of A times the mass of B, divided by the square of the distance between A and B. So it's called the inverse square law. So the farther apart they are, the weaker the gravitational force. But the force is proportional to the mass of A times the mass of B. And this G, you don't really have to know the number, but big G is 6.67 times 10 to the minus 11 in SI units. So that must be newtons meters squared per kilograms squared, if I did that right. So now we can talk about the kind of interesting case when we have a satellite going around Earth. And one case Richard Muller talks about is a satellite in low Earth orbit. That's where the orbit of the satellite is, the satellite's only a short distance above Earth's surface. So effectively the radius of the orbit equals Earth's radius. So we can do that. So then, okay, the force that keeps the satellite in motion equals this gravitational force. And one of the two objects is Earth. So then we're going to say the force of Earth on the satellite, gravitational, is, so this is big G, and then we have the mass of Earth, and we have the mass of the satellite, and then we're saying if it's low Earth orbit, means that our Earth satellite is approximately the radius of Earth. It's just a little bigger. So this is basically radius of Earth squared. And that equals the mass of the satellite times the speed of the satellite divided by, and again, the radius of this orbit is our Earth because we're saying it's just maybe a few miles above Earth's surface. So now you can notice that the satellite mass cancels out, and we could get 1 power of Earth's radius to cancel out. I guess we could do that. Oh, we can use what the heck? Let's use a nasty trick, which is that it turns out that big G times the mass of Earth times the mass of some satellite, and if it is at Earth's radius, so when you're standing on Earth, right at Earth's surface, the gravitational force between you and Earth just equals your mass times little g. That's that 9.8 meters per second per second. Again, this is only because you're right at Earth's radius. So actually I think I didn't want to do this cancellation. Let's undo this cancellation. Leave that squared. We'll keep this here. What the heck? I think then we're saying the velocity of the satellite squared divided by Earth's radius, this is for low Earth orbit, just equals, see the ms cancels here. If we wanted to, we can cancel the ms there. This just equals little g. So I guess then you could say, how fast is a satellite moving around the Earth? You say, okay, v satellite is the square root of little g times our Earth. That seems to be 9.8 meters per second squared. And Earth's radius is 6,400 kilometers, so that's 6.4 times 10 to the 6th meters. There's the 1/2 power. 6,400 kilometers, that's 6.4 million meters. So let's see what we get. Our check on all this is going to be that it takes about 90 minutes. We know it's about 90 minutes to go around. Square root of 9.8 times 6.4, 10 to the 6th. So 7,900 meters per second roughly. You don't really have any, usually you only have intuition for things that are kind of your natural, like kilometers per hour, miles per hour. So this is approximately 7,920 meters per second. So then the question is, how long does it take to go around Earth? Let's see if we got this right. You say, okay, I want to go all the way around Earth. So that's a distance of 2 pi times r Earth. That's how far I'm going, and I'm going at a speed of v. So you say the orbital period, the time it takes to go all the way around, must be 2 pi times the radius of Earth divided by this speed. Does that make sense? Because there's meters meters divided by meters per second, so you get seconds. That seems good. Let's plug that in. Let's see if this works. This is kind of an indirect way to get this number, but I think it could be kind of fun. So 2 times pi times 6.4 10 to the 6, and then we're going to divide that by 7920. And that says 5077. We divide by, so that's 5077 seconds. And we divide that by 60 to get minutes, and it gives us 85 minutes. I think that's right. Yeah. So I remember from childhood watching the space shuttle launches that it takes about roughly 90 minutes, maybe it's just a little under 90 minutes, for a satellite in low Earth orbit to encircle the Earth. So we did it. 85 minutes. Okay, the next thing I want to do, I'm going to do some erasing. The next thing I want to show you, and again, you don't have to be able to reproduce this, but maybe you can follow it. I want to show you what happens when we say the satellite goes around exactly once per 24 hours. Because that's a so-called geosynchronous or geostationary orbit. So let me do that. Let's consider that we have a satellite going around and around Earth, and the force that's keeping the satellite going around in circles is the gravitational force between the satellite and Earth. But now let's suppose that the satellite goes around Earth exactly once per 24 hours. And if it does that above the equator, then the satellite will always appear to be at the same place in the sky. And that's really useful for satellite-based television, satellite-based internet, satellite. It's actually less useful for internet because it's a pretty long trip back and forth, but you can potentially use it for satellite-based internet. You can definitely use it for TV broadcast where you want your satellite television or your satellite radio. This is between Earth and the satellite. Here's the mass of Earth. Here's the mass of the satellite. Now this is the distance between Earth's center and the satellite. And then this is going to be the mass of the satellite. So again, the centripetal force is provided by the gravitational attraction between Earth and the satellite. So we're going to say big G times the mass of Earth times the mass of the satellite divided by the radius squared equals the mass of the satellite times the velocity or the speed of the satellite squared divided by, this is this radius between Earth's center and the satellite. mv squared over r is gmm over r squared. And what can we do with this? Somehow we want to say that the period of the orbit, so this is 2 pi times the distance traced out by the circle divided by the speed at which it goes around. We want this to be 24 hours, which is 86,400 seconds. It's just 60 times 60 times 24. Turns out to be 86,400 seconds. Let's see. We can cancel the mass of the satellite. We can cancel one power. So I want to figure out how far away from Earth's center do we have to be. And it's going to turn out to be about 7 Earth radii to get these two equations to be simultaneously true. I guess the math isn't so exciting. We can solve both of them for v and set them equal. Yeah, so in this case, we have v equals 2 pi r divided by 86400 seconds. And here we have v is, so this is, it's all on the right side. We take the square roots, we get the left. So this seems to be the square root of big G times the mass of the Earth over the radius of the orbit. So somehow that is going to be the same as 2 pi radius Earth satellite divided by 86400 seconds. And we want to solve for r now. Okay, I'm going to put all the r's in the same place. We can say, we can move a half, see this is r to the half power. So this seems to be r to the 3/2 power. We can cancel that out because we have a square root of r moves over there. R times square root of r to the 3/2 power. That's going to do it for us. So we have r Earth satellite to the 3/2 power equals 86400 seconds divided by 2 pi. Again, you won't really do things this complicated. Times the square root of big G times the mass of Earth. So that's all fine. So we take this whole mess and we're going to raise it to the 2/3 power, and that's going to be r. Let's try it. We'll plug in some numbers. We said G was 6.67 10 to the minus 11 in SI units. Mass of the Earth is 6 times 10 to the 24 kilograms. 6 times 10 to the 24 kilograms, that's mass of Earth, times 6.67 times 10 to the minus 11, that's the gravitational constant. And then all that stuff is going to be the square root of, and then we're going to multiply that by 86400, and we're going to divide by 2 pi. And we're going to raise that whole thing to the 2/3 power. Okay, I get something like 4.3 times 10 to the 7th meters equals the radius. That's not very meaningful. Let's try how many Earth radii is it? So RES divided by Earth's radius. That tells you how high it is in terms of Earth's radius. So we'll take that divided by, so Earth's radius we said was 6.4 times 10 to the 6th meters. Oh, cool. Yeah. So it's like 6.6. So this is approximately 6.6 Earth radii. Yeah. So if you want to say how far above the center of Earth is a geostationary orbit, it's something like 6.5. The number I had remembered was 7. I guess it's more like 6.5. So here's Earth. You say, how far above Earth do you have to be so that you go around once per 24 hours? So if you're over the equator, you appear to be just standing in one place. And it's actually pretty serious. 1, 2, 3, 4, 5, 6.5. It's like that far out. It's pretty big. It's like way out there to scale. Like there's Earth's radius. You have to be way out there to be in a geostationary orbit. I think that's kind of surprising. Kind of surprising and interesting. Okay, again, that's like more complicated than you're really going to have to do, but it connects to the Richard Muller reading, so I thought it was worth going through on the lightboard.
So, a famous physics problem says a rock, a big massive rock, is suspended from a fine thread. So there's this little bungee cord here. You're going to ignore this bungee cord is just so if the string breaks, things don't fall and damage anything. The famous physics problem says a rock is suspended by a fine thread. An identical fine thread is hanging below the rock. And the question is, if I pull on the bottom string, which of these two strings is going to break first? And there are two conditions. One condition is I pull gently on the string, and the other condition is I pull really quickly, very hard. I pull as hard as I can on the bottom string. And the question is, which one will break first, and will the answer depend on whether I pull gently or really pull hard? So you can sit and ponder it. We may eventually work through the math, but I think I'm going to do the pull really fast first. Let's see what happens when I pull really fast. So when I pull really fast, it seems like the bottom string breaks. All right, that's pretty good. Now I'm going to retie the bottom string. Okay, now let's try the exact same thing where instead of yanking really quickly, I'm going to pull very slowly on the bottom string. And then you want to think which string is going to break first. Okay, pulling gently. Oh, look at that. Seems like when I pulled gently, the top string broke. But when I pulled very quickly, the bottom string broke. And then we'll go to the lightboard and we'll think about why did that happen. Let's try it one more time. So I'll pull really fast, and the bottom string breaks. Then let me retie that same string. Now I'll pull gently. The top string breaks. Okay, think about that.
Ready? Yeah. So here's the famous physics problem from the demonstration. I have a rock of mass m, and it is suspended from the ceiling by an upper string. I'll call that string A. And then down beneath the rock I have an identical string, string B. And I am pulling down on string B. And I have two ways I can pull down. I can just pull down gently, slowly, on string B, or I can yank string B really quickly. And the question is, under these two circumstances, which string breaks first? So I guess there are two identical strings. The string can sustain some force. So remember, what does a string do? A string transmits a force from one end of the string to the other. So whatever that force is on one side, it's the same force on the other side. So that force transmitted by the string we call the tension in the string. And if you pull too hard so that the tension is very, very big, then the string breaks. So there's some maximum tensile strength of the string. So we could just say, well, if one of these two strings has a tension which is considerably bigger than the other, then that seems to be the string that's going to break first. So let's first analyze with a free body diagram the case where I just pulled gently on the bottom string, string B. So let's draw a free body diagram for, I'm going to call this the block. Right, so here's the block. Rock, the block. I guess I called it a rock, now I'm calling it a block. Okay, let's call it the block. So here's the block. Okay, what is a force acting on the block? How about Earth's gravity? So we have the gravitational force exerted by Earth on the block. Earth on the block. I guess I'll use little b for block. That's basically the mass of the block times little g. Whatever that is. Then I have whatever force is exerted by the lower string with which I'm pulling. I guess we don't know exactly how hard I'm pulling, but let's say, well, it's probably pulling some decent fraction of the block's weight. So let's say I'm pulling with a force kind of like that. So this is the contact force, which is by string B on the block, and that force equals the tension in string B. And then let's say I'm pulling very slowly, so the block its acceleration is negligible, it's barely budging. Then it seems like no matter what's happening, there's another arrow pointing up. And I guess, well, I'll just make that arrow go all the way up to the top because that's about as long as I can make it on this board. And this is the contact force by string A on the block. This is the block B. That equals the tension in string A. So, and then we can say that the acceleration of the block is 0. So let's say the acceleration of the block is 0. Okay, so if that's true, if the acceleration of the block is 0, then Newton's second law says mass of the string times 0 equals the vector sum of all the forces on the block. So we'll do up minus down. So that tells us that the tension in string A minus the tension in string B minus m of the block times g equals 0. That's just the sum of all the forces up minus down. It's 0 because we're saying the acceleration of the block is 0. So that tells you that TA equals TB plus the weight of the block. So TA is always bigger than TB. So if I pull slowly enough that the acceleration of the block is negligible, then the tension in the upper string is always mg bigger than the tension in the lower string, so the upper string has to break first. Now what happens if I pull really fast? So let's challenge the assumption that the acceleration of the block is 0. In fact, you can see, if you look carefully at the really fast motion, the fast yank videos, then you can see, and I also did like little skateboard versions, so you can see that the string does cause, when the string goes taut, it does cause the block to start oscillating up and down, so it causes it to accelerate. You can see it with the version with the skateboard, it causes the other skateboard to accelerate a little bit, or you can see with the slow motion video that after the pull, you can see it does displace the block a little bit, because then afterwards the block is kind of bouncing up and down a little bit. So there is a non-zero acceleration. So let's challenge this assumption. So we'll say, okay, I don't like this assumption anymore. And we're going to say, here's the acceleration of the block. And it's pointing downward because I pull the string hard enough that I start to accelerate the block. So when I do that, initially, before the lower string went taut, the tension in the upper string must have been exactly equal to the weight of the block. So you imagine, okay, the lower string is just slack. I'm kind of up here. I haven't started pulling down yet. So the string, this lower string is slack. It's not taut yet. So then this upper string is simply supporting the weight of the block, and the tension in this lower string is 0. So here's the case before this string goes taut. So this weight of the block is just balanced by the tension in string A. But now I'm going to pull as hard as I can on the lower string. Okay, I'll pull like that, let's say. And you say, how can I do that without breaking the top string? Well, and the thing is, I'm pulling so quickly that this block starts to accelerate. So this equation is now wrong because the acceleration is not 0. So instead, this is Newton's second law for the block. That's what we wrote before, except the acceleration was 0. So this is the sum of the forces in y on the block. That was what it was before also, except that the sum happened to be 0. And this is the mass of the block times the vertical acceleration of the block. Okay, so it would be positive if the block's accelerating upward. It's negative if the block's accelerating downward. The block will accelerate downwards. This is going to be some significant negative number. Remember this. So this acceleration in the y direction is going to be a negative number. So let's solve for the tension in string B now. So the tension in string B is, so I'll move this over to the other side. So tension in string B is the tension in string A minus the mass of the block times G, and then minus the mass of the block times this vertical acceleration of the block. But remember, this vertical acceleration is negative. So we know that AY is less than 0 because we're accelerating the block downward. I'm almost tempted to write the absolute value of this thing. Maybe I'll do that. I'll just say minus AY, because then minus AY is a positive number. How about that? So we'll say the tension in string B is the tension in string A now plus the mass of the block times, and then you see this is, so minus AY is a positive number. Here's minus AY, which is a positive number, and then minus G. Yeah, that's a little confusing. Maybe I should have just said AY is the downward acceleration. So basically, if this downward acceleration of the block is bigger than G, which, it should be, that's reasonable as long as if I pull fast enough that this downward acceleration of the block is bigger than this gravitational acceleration G, then the tension in string B is bigger, so string B should break first. So that's what distinguishes the two cases. If I pull string B slowly so that the acceleration of the block is tiny, or if at least the acceleration of the block is smaller in magnitude than little g, then the top string breaks first. But if I yank on the string so quickly that the block starts to accelerate with an acceleration bigger than g, a downward acceleration bigger than g, then the tension is bigger in the bottom string, and the bottom string breaks first. So here's a problem that's a little bit like that lowering the bucket problem from last week. I have a fish. Let's say, apologies to any vegetarians out there. Let's say I caught the fish. Here's a fish hook, and there's the fish hooks on the end of a string. So here's a string, and the tension in the string, what is the force exerted by the string on the fish? So that's equal to the tension in the string. And then I have a scale up here. It's like a fish measuring scale. Often you hold one end, and then you dangle the fish on the end of the scale, and the scale reads out the weight of the fish. I guess you can kind of intuit that the reading on the scale will be the same as the tension in the string. So the scale is really just there to tell me how much force is the string exerting on the fish. So the scale is it's like a way to read out this string tension. If we draw a free body diagram for the fish, then here's the fish. Okay, let's say the acceleration of the fish is 0. So what do we have for forces on the fish? Well, there's the weight of the fish. So here is F, gravitational, exerted by Earth on the fish. So that's just the mass of the fish times little g. And then there's the tension in the string. So that is the contact force by the string on the fish, which is just the tension in the string. And if the acceleration is 0, these two forces must be equal in magnitude. And then the scale just reads the weight of the fish. Now, let's do something a little trickier. Let's put the whole thing in an elevator. So we'll say, here is my elevator, and this is the ceiling of the elevator. So everything is inside an elevator. And let's say the elevator has some upward acceleration, a sub y. So if the elevator is accelerating upward, then a sub y is positive. And if the elevator is accelerating downward, then a sub y is negative. So we'll just take a sub y to be positive. If we want it to accelerate downward, we'll just plug in a negative value. Okay, so now we say that the acceleration of the fish, the fish is going to travel with the elevator. So the acceleration of the fish now points upward. It's the same as the acceleration of the elevator. So in that case, it seems like to make the fish accelerate upward, This arrow is not, it can't change because the actual weight of the fish doesn't change, its mass doesn't change, but somehow what the scale reads will change. If you want the fish to accelerate upward, then somehow this tension in the string, which is going to be the same number as the reading on the scale, has to be bigger than the weight of the fish. And now the fish will accelerate upward. And if we write Newton's second law for the fish, we say Newton's second law for the fish. It says the mass of the fish times the vertical acceleration, that's upward, the upward acceleration of the fish equals. So this is the sum of the forces in the y direction acting on the fish, up minus down. So that's the tension in the string minus the mass of the fish times g. And then you want to say, what does the scale read? So the tension in the scale is basically the same as the tension in the string. So scale just reads whatever the tension in the string is. So you say, what does the scale read? The scale reads this tension here in the string, because the string just transmits the same force from one end of itself to the other. So that's the force on the scale. So this tension, which is what the scale reads, the scale reads tension equals the mass of the fish times ay plus g. Yeah, actually that's worth circling, squaring. So what does that tell you? That tells you that if the elevator is not accelerating, so maybe it's just standing still, maybe it's moving at constant velocity. So usually an elevator, you can feel it in your gut, right? Usually the elevator starts upward, you can feel that, and then it's just moving upward at constant velocity, so you don't feel that. Maybe you can hear the wind, but you don't feel it. So when the elevator is not accelerating, the scale reads just the weight, ordinary weight of the fish. If the elevator is accelerating upwards, this is a positive number, then the scale reads a number bigger than the weight of the fish. And if the elevator is accelerating downwards, so this is a negative number, then the scale reads a number smaller than the weight of the fish. That's also true. This exact same thing is true if you're standing on a bathroom scale in the elevator. So if I were to say, here's the floor of the elevator, and I put like a bathroom scale down, and then I stand on that. So here I am, me, here's a bathroom scale, and we are all for some whatever. Actually, I've done this in DRL, and they're all in the elevator. So if we're inside an elevator, then you say, what does the scale read? The scale is going to read my mass times the vertical acceleration of the elevator plus g. And you do it the exact same way. I draw a free body diagram for me. There's gravity downward, and the scale is pushing up on me. To make me accelerate upward, the scale has to push on me with a force bigger than my weight. To make me accelerate downward, the scale has to push up on me with a force smaller than my weight. And then you just solve for the force exerted by the scale. That's what the scale reads. The scale reads the force that the scale exerts. Then the force exerted by the scale on me, which is the same thing as the number that the scale will read, is my mass times little g plus the upward acceleration. So if the elevator is accelerating upward, so let's say g is 9.8 meters per second squared, then it's my mass times 9.8 meters per second squared. If the elevator is accelerating, that's g, right? G is 9.8 meters per second squared. So if the elevator is accelerating upward, say at 2 meters per second squared, then it would be my mass times 11.8 meters per second squared. If the elevator is accelerating downward at 2 meters per second squared, then it would be my mass times 7.8 meters per second squared is what the scale reads. So if the elevator is accelerating downward, then the scale reads something smaller than my usual weight. If the elevator is accelerating upward, then the scale reads something bigger than my usual weight. You kind of can see that because if you're accelerating upward in an elevator, then your stomach feels a little bit heavier than usual. And if you're accelerating downward in an elevator, then your stomach kind of feels a little light, like it's kind of trying to bounce upward. It gets even a little trickier when you say, when you say everything's in an elevator, the way you work those problems is you do the exact same thing you would do just to draw a normal ordinary free body diagram for the object of interest, a fish, or for me. But then the acceleration is the same as the acceleration of the elevator. So you say, okay, the fish is accelerating at whatever acceleration the elevator has, or I am accelerating at whatever acceleration the elevator has. So then the forces don't add to zero. The forces add to the mass of me times my acceleration, or to the mass of the fish times the fish's acceleration. And you have like up minus down. So then usually you want to solve for the force read by the scale. So if you do that, you solve for t and collect terms together. You say, aha, the tension is, if the elevator is accelerating up, the tension is a little bigger than the fish's weight. The elevator is accelerating downward, the tension is a little smaller than the fish's weight. you want to intuit, oh yeah, it makes sense that the tension's a little bigger versus a little smaller, but then you want to go through and systematically do it with the free body diagram, Newton's second law, solve for what the scale reads. So we'll do maybe like 1 or 2 examples of that on Monday. Just, it's one more example of just practicing using Newton's laws to wake up your physics brain, and then we'll move on to the new Physics 9 topics.